Hello, everybody. Welcome to your first of 3 lectures on Chapter 11, Impulse and Momentum. Today, what I'd like to do is just quickly talk about what I'm going to be covering in Chapter 11. And then today, specifically, I want to talk about momentum and impulse and the impulse-momentum theorem. So this is the very last chapter we're covering before our first celebration, and it's Chapter 11 on impulse and momentum. So, like I said, today what I'm going to talk about is what the definition of impulse is. And as a little preview, impulse is a vector quantity, and it ends up being equal to the mass of the object in kilograms times the velocity in meters per second. And impulse, I'll kind of go through that today, but we use the symbol J for impulse. I have no idea why we use the symbol J, but that's the symbol that we use. And what we're going to see is it's defined as the integral of the force on an object times the time over which it acts from the initial time to the final time. And what we're going to see today is that the impulse on an object ends up being equal to the change in momentum of the object. So that's what I'm going to focus on today. On the second lecture, which will be tomorrow on Thursday, I'm going to look at conservation of momentum. And this is one of the giant laws of physics. Conservation of energy, conservation of momentum, you're going to be using throughout your physics career. If I have time tomorrow, I'll talk a little bit about collisions, but then the very last lecture, I'm going to be talking about collisions and explosions, which is really just conservation of momentum. And then if I have time, I'm going to talk about momentum in 2 dimensions. It's really just conservation of momentum applied in the x direction, conservation of momentum applied in the y direction. I'm not sure yet whether or not I'm going to include this on the second celebration. We'll see sort of how far we get. Okay, so what I want to do is actually just start off with a question for you. So the question is this, and I have it written right up here. So imagine I have a ball which is traveling to the left, it strikes a rigid wall, and then bounces back to the right. So the situation is here. I've got, let's do a little draw. Okay, never mind. So I've got a ball which is moving to the left. It hits a wall. The wall's exerting a force on it for some small amount of time, and then the ball ends up rebounding to the right. So a quick little question for you. If I was to plot the force that the wall exerts on the ball as a function of time, what would that plot look like? Well, up until now, we have pretty much been considering all forces to be constant in time, meaning the force is not changing how many newtons it's exerting. So we sort of have been modeling this like, so let's say this is where the collision starts, and this is where the collision ends. And I'm going to draw sort of the correct graph and the incorrect graph. So we have been assuming that the force that one object exerts on a second object is basically constant. And what we're going to see is for most real life forces, that is not the case at all. So if I were to do a more realistic plot of what the force that the wall exerts on the ball as a function of time looks like, what it would be is, this is before it hits the wall. Oops, get out of there. Once it hits the wall, then what happens is the force starts at 0, goes up to some maximum value, decreases back to 0. And what I would see is the force is most definitely not constant with time. The force starts at 0, increases to some maximum value, and then decreases back to 0. So here's a figure I got from your book. Shows the exact same situation. I have a ball which is approaching the wall to the left. It collides with the wall, and the wall exerts a force on the ball for a certain amount of time, delta t. Then as a result of that, the ball rebounds and then ends up moving in the opposite direction. So this is what a plot might look like of the force of the wall versus time. Again, it starts at 0, increases to some maximum value, and then decreases back to 0. Now, this plot is showing that the force is symmetric, meaning I have this nice, beautiful curve that looks the same on the right as it does on the left. More realistic is it's not going to be exactly symmetric. It might look something like what I've drawn here, which even then looks somewhat symmetric. But here, let me just say, this is showing compression and expansion. I'm going to show you a pretty cool video in a second, but what's happening is if this is the wall, the ball is coming in, and as it hits, the ball is actually compressing a bit until it reaches a maximum compression, and then it starts to expand as it's moving in the opposite direction. So let me show you a couple of videos and show you what I mean by this. So one, this is a video of a golf ball traveling at 150 miles an hour that's being filmed with a camera that can film at 70,000 frames per second. So let me pause this for a second. Oh, I want to restart that again, but I wanted to make it bigger. Okay, let me stop this one more time. Okay, so here's a collision of a golf ball with a steel plate moving at 150 miles an hour, framed at 70,000 frames per second. That is badass. Actually, let's just play that whole thing one more time because it's pretty darn cool. Now, I know what you're thinking. Get the hell out of here. That's not a real video of a golf ball hitting a steel plate. Welp, you are correct. This is not really a typical golf ball hitting a steel plate. What it is sort of a rubber ball that looks like a golf ball. Let me show you a more realistic video of what a golf ball hitting steel in slow motion looks like. And let's just see one more. Here's a golf ball hitting a golf club at 100,000 frames per second. So what you hopefully see in these real videos is when the golf ball is impacting the golf club or the wall, one, the ball starts to compress as it hits the wall or the golf club, reaches some maximum compression, and starts to expand again. And again, if I were to plot the force on the ball as a function of time, what I would see is the force is most definitely not constant. It's not a horizontal line. The force starts at 0, increases to some maximum value, and then decreases back to 0. Now, if we were to try and analyze the motion of this ball by looking at the acceleration and figuring out how the velocity changes, we'd have some challenges because the force is not constant. But what we're going to do is actually use Newton's second law to derive what's called the impulse momentum theorem. And this is going to help us look at what is the effect of a force on an object when the force is not constant in time. So again, we're going to start looking at more realistic forces that aren't constant. They start at 0, they increase to some maximum value, and then they decrease back to 0. So let's actually analyze this. So I'm going to start just with Newton's second law. And we know the sum of the forces on an object equals the mass of the object times the acceleration, which is just the mass times the derivative of the velocity with respect to time. Now, for this particular example, we only have one force. We're just assuming, let's say, the force of the wall and the ball. So instead of the sum of the forces, I'm just going to write this as Fx. It's just one force. And then we're only looking at the change of the velocity in the x direction. And just to be specific that this force is not constant and it's changing in time, I'm just going to write this as the force in the x direction, which is a function of time. I'm not multiplying by time, it's just the force is a function of time, equals m times the derivative of the velocity in the x direction with respect to time. So this is really just Newton's second law written out in one dimension, where we only have one force acting on the object. Now remember, I can do anything to both sides of an equation without changing the value of the equation. So what I'm going to do is I'm going to integrate both sides of this equation by dt, by time, and I'm going to integrate it from some initial to some final time. So left-hand side, I've got the integral of the force integrated with respect to time from some initial time to some final time. And for this particular example, this time is during the collision. So t initial is when the collision starts, t final is when the collision ends. And this equals the integral from t initial to t final of m times dvx dt times dt. Now, let's first focus on this right-hand side. So if I'm taking a function and taking the derivative of that function and then integrating it, what I get is just the original function. So if I take the derivative of velocity with respect to time, and then I integrate that with respect to time, what I basically end up with is velocity back. So this right-hand side, so one, I can pull out the mass. We are going to assume the mass is constant and not changing. So what I have is m times the integral from t initial to t final of derivative of velocity in the x direction with respect to time integrated dt. So the derivative of the velocity with respect to time integrated with respect to time basically gives me the velocity function back. And so what I end up with is this is equal to m, and then what I end up with is the velocity in the x direction basically evaluated from some initial time to some final time. Well, by definition, our velocity at some initial time is just our initial velocity. Our velocity at some final time is just our final velocity. So this right-hand side becomes m times the final velocity in the x direction minus the initial velocity in the x direction. That's basically what the right-hand side is. So again, if I have a function that I take the derivative of that function and then I integrate that derivative, I get the original function back. So for this right-hand side, from m dv dt, I integrated both sides with respect to time. We haven't looked at this left-hand side yet, but this right-hand side, m is constant, so I can pull it out of the integral, and I have the integral dvx dt integrated over dt. So I basically end up with my original function, which I would evaluate at some initial time and some final time. Well, velocity at the initial time is just my initial velocity. Velocity at the final time is just my final velocity. So this right-hand side basically has this quantity m times the final velocity in the x direction minus m times the initial velocity in the x direction. Well, we define this quantity, mass times velocity, as momentum. And the symbol that we use for momentum is p. So momentum, p, is equal to the mass of an object times its velocity. So momentum is a vector, which means I can break it up into x, y, and z components. So this equation is really three different equations in one. It's the momentum in the x direction equals mass times velocity in the x direction. Momentum in the y direction equals mass times velocity in the y direction. and momentum in the z direction equals mass times velocity in the z direction. So the other thing is momentum is mass, which is a scalar, which is always positive, times velocity, which is a vector. Well, when I multiply a vector by a positive scalar, I could increase or decrease the length of the vector, but it doesn't change the direction. So what that means is the direction of the velocity vector and the direction of the momentum vector are exactly the same. So P as a vector points in the same direction as the velocity vector. So this left-hand side we still haven't dealt with, but the right-hand side is mass times final velocity in the x direction minus mass times initial velocity in the x direction, which is really my final momentum minus my initial momentum in the x direction. So rewriting the left-hand side, let me go down a little bit here. We've got the integral from some t initial to t final of fx dt equals my final momentum in the x direction minus my initial momentum in the x direction. And I'm not putting little arrows over momentum to indicate that it's a vector because I've indicated that we're looking at the x component of the momentum. I can only look at x, y, and z components of something if it's a vector. So this right-hand side is just the change in the momentum in the x direction. Final value minus initial value. Well, this left-hand side, the integral of f dt, in this case, the integral of fx dt, this is the definition of impulse. This is how impulse is defined. Just like we defined work as the area of fx dx, impulse is defined as the area of fx dt. It's the overall effect of the force acting on this object over a given time. So what you hear of as impulse momentum theorem is the following. The impulse on an object equals the change in momentum of the object. This is the impulse momentum theorem. The impulse on an object, which is equal to the integral of the force dt, equals the change in momentum of the object. So you can write this different ways. This is sort of just the quick and easy way of writing it. But this is also a vector equation, which means I could look at this in the x, y, and z directions. So let's just focus on x and y. So this is really saying that the momentum in the x direction equals the change in momentum of the x direction. I'm sorry, the impulse in the x direction equals the change in momentum in the x direction, or the impulse in the y direction equals the change in momentum in the y direction. Now the impulse is always equal to the integral of the force with respect to time from some initial time to some final time. So for example, let's look at this. Impulse in the x direction equals the change in momentum in the x direction. Well, the impulse in the x direction is the integral of fx dt from some initial time to some final time. And my change in momentum in the x direction is my final momentum in the x direction minus my initial momentum in the x direction. So this is p final in the x direction minus p final, sorry, p initial in the x direction, which equals m v final x minus m v initial x. So that is the impulse momentum theorem. Momentum, the mass of an object times its velocity. Impulse is the area under the curve of force integrated with respect to time. And one thing I didn't tell you, what are the units of impulse? What are the units of momentum? Well, since momentum is just mass times velocity, the units of momentum have to be the units of mass, which is kilograms, times the units of velocity, meters per second. So the units of momentum are the kilogram meters per second. Well, how about the units of impulse? Well, impulse is basically the integral of a force dt. So the impulse has to have units of force times time. Units of force is Newton, units of time is second. So the units of impulse are the Newton second. And these two units are equivalent, meaning a Newton second, keep in mind a Newton second is a kilogram meter per second squared, which is a Newton, times a second, which is the same thing as a kilogram meters per second. However, even though these two units are equivalent, you generally never use kilogram meters per second for units of impulse. We always, get a new color here, we always use kilogram meters per second for the units of impulse, Newton seconds for the units, strike that, reverse it. We always use kilogram meters per second as the units of I've been on Zoom too long today. We always use, one more time. We always use kilogram meters per second as the unit of momentum, and we always use Newton seconds as the unit of impulse, even though they are equivalent. Okay, so let me just go to my lecture notes that I gave last year and just kind of do a quick little recap of everything I just touched on. So, forces in general are not constant. They change as a function of time. Most real-world forces are not constant. They vary. And if I were to look at the force versus time for, say, a collision, what I would see is, like I was showing you before, the force starts at 0, increases to some maximum value, and then decreases to 0. If I want to know what is the overall effect of this force, that's when we're going to start using the impulse momentum theorem. So the derivation basically just starts with Newton's second law, sum of the forces equals ma. And I did it here in a slightly different way, but the end result is, what you end up getting is, on the left-hand side, I end up with this integral of fx dt. This is the definition of the impulse. And on the right-hand side, I end up with this mass times final velocity in the x direction minus mass times initial velocity in the x direction. Momentum is how we define this quantity of mass times velocity. So this is the definition of momentum. And it is a vector, and the direction of momentum is the same as the direction of the velocity. So, for example, let's say I had a 10 kilogram mass, which was moving to the right at 2 meters per second. And I want to know, what is the momentum? Well, momentum, and in this case, if we're talking about the x direction, would be mass times velocity in the x direction. So in this case, it would be 10 kilograms times 2 meters per second. And if I want to be specific about direction, I can include the unit vector. So what I get is the momentum is 20 kilogram meters per second in the I direction. So I guess if I want to be specific, if I just said px, the momentum in the x direction, I would not need to include my unit vector because I'm already indicating that that's the momentum in the x direction. So perhaps I shouldn't put that I. But if I was just saying what is the momentum of this object, then I could say 20 kilogram meters per second in the I direction. So like I was saying, momentum is a vector equation, which means P equals mv, in a sense, is really three equations in one. It's momentum in the x direction equals mass times velocity in the x. Momentum in the y direction is mass times velocity in the y. And momentum in the z direction is mass times velocity in the z direction. So our impulse momentum theorem states that the impulse on an object, which is defined as the integral of f dt, equals the change in momentum of the object. And again, this is a vector equation. So this is sort of the impulse momentum in the x direction. If I wanted it in the y direction, it'd be the integral of fy as a function of time dt, again, from t initial to t final, equals, in this case, it would be the change in momentum in the y direction. So one last thing. Oftentimes, rather than looking at the, and actually let me go back to April 15th, rather than looking at the area under the curve of f versus t, oftentimes what we want to look at is what is the average force. And so there's another equation for impulse. And let me first, well, let me just write it down here. So impulse is defined, and again, let's just do it in the x direction, as the integral of fx dt from some initial time to some final time. But that is also equal to the average force in the x direction times the time over which that force is acting. Now, how do we define the average force? Well, if this is my plot of force versus time. So here's my time in seconds, and here's my force in the x direction in newtons. And let's say here's where the collision starts, or the force starts. Here's where it ends. So what I would see is, let's say the real force looked like this. Started off at 0, went up to some maximum value, then decreased back to 0. Integral of f dt is really just the area under the curve of force versus time. So if I want the impulse, it's really just the area under this curve of force versus time. Well, how do you think we would define the average force? And what it is, the average force is the constant force that would give me the same area under the curve as the real force. So my average force, let me do this in blue, draw. My average force, I'm assuming that my force is constant. And the average force is the constant force that would give you the same area under the curve of the real force versus time. So in red, that might be the real force versus time for a collision, but the average force is a constant force that when I take the area under the curve, gives me the exact same area as the real force. So in this case, the average force in the x direction times delta t will give me the same area as the real force integrated dt from t initial to t final. So forces aren't really constant. They start off at 0 and they increase to some maximum value. But oftentimes we want to look at the average value. So in summary, impulse momentum theorem says impulse equals change in momentum. And again, we can look at this in the x direction or the y direction. The impulse in the x direction equals the change in momentum in the x direction. The impulse in the y direction equals the change in momentum in the y direction. Now, impulse, I can now look at two different ways. If I'm looking at the impulse in the x direction, it is the integral of the force in the x direction, dt, evaluated from t initial to t final, and that is also equal to the average force in the x direction times delta t. So two different ways. So keep in mind also this integral f dt, this is equal to the area under the curve of f versus t, or in this case, fx versus t. Whew, that ended up being about a half hour, a little bit longer than I wanted to. So I'm not going to do any example problems in this lecture. On Thursday, tomorrow, I will sort of just recap what I just covered, do some example problems, and then move on to conservation of momentum. So that is it for today. Big concepts. Momentum is the mass of an object times the velocity of the object. The units of momentum are kilogram meters per second. Momentum is a vector, and it points in the same direction as the velocity. And impulse is sort of the overall effect of a force over time. Most forces aren't constant. They start at zero and they increase to some maximum value and then they decrease back to zero. Impulse, is defined as the area under the curve of the force integrated with respect to time, f dt. Another way of writing the impulse, it's the average force times the time over which the force acts. The unit of impulse is the Newton second. The unit of momentum is the kilogram meter per second. Those two units are equivalent. A Newton second is the same as a kilogram meter per second, but we always use kilogram meter per second for momentum. We always use Newton seconds for impulse. That is it. Happy Wednesday.